This video, we will discuss the principle of Raman effect and understand how it can be used in Raman spectroscopy to perform analysis on a given sample. Let us first understand the Raman effect. When a sample is exposed to a monochromatic light in visible region, the sample absorbs light and major portion of the light gets transmitted through the sample. However, a minute part of the light is scattered by the sample in all the directions. One can observe the scattering at right angle to the incident beam. The incident light has a particular frequency. If the scattered light has the frequency same as the incident light, then the scattering is called as Rayleigh scattering. However, it has been observed that about 1% of the total scattered intensity occurs at frequencies different from the incident frequency. This is called as Raman scattering. Raman scattering can be thought of as two-photon process. The electrons have different vibrational levels. They are defined by specific energy differences. When an incident monochromatic light interacts with an electron in the sample, the electron absorbs energy from the incident photon and it rises to a virtual state of energy. The energy transferred is given by the formula E equals h nu, where nu is the frequency of incident photon. The electron then falls back to an energy level by losing energy. If the energy lost equals to the energy of incident photon, the electron falls back to its initial level and in this process emits another photon. Since the energy lost is equivalent to the energy of incident photon, the released photon has same frequency as the incident photon. As the frequency is same, Rayleigh scattering occurs. However, sometimes electrons, when losing energy from the virtual state, can fall back to a different vibrational level. In this case, the energy lost by the electron is different than the energy absorbed from the incident photon. As a result, the photon emitted by the electron has energy different than the incident photon. This is possible when the frequency of the emitted photon is different than the incident photon. This gives rise to Raman scattering. Depending upon the final energy of the electron or final vibrational level of electron, Raman scattering can be separated into Stokes line and anti-Stokes line. If the frequency of scattered photon is less than the frequency of incident photon, Stokes lines are observed on Raman spectrum. This happens when the electron absorbs energy. Similarly, when frequency of emitted photon is greater than incident photon, anti-Stokes lines are observed. This means that energy is released by the electron. The Raman spectra gives the molecular fingerprint and it is different for different molecules. By studying the spectra, one can identify the rotational levels and thus a particular molecule. This helps in performing qualitative analysis. Similarly, the intensity of a particular Raman line helps one determine the concentration of a molecule in a sample. In this manner, quantitative analysis can be done. Thus, Raman spectroscopy can be used to perform both qualitative and quantitative analysis on a sample.